RSA encryption is one of the most popular encryption techniques used widely across the internet today. RSA encryption involves three numbers: the modulus, the public exponent, and the private exponent. The idea is the modulus n and public exponent e can be used to encrypt a message, whereas n and the private exponent d can be used to decrypt it. To see how it works, start by picking two primes and let the modulus n be their product. Let the public exponent e be a number coprime to p-1 times q-1. Because e is coprime to p-1 times q-1, we can find an integer d that multiplies with e to give 1 mod p-1 times q-1. Fermat's little theorem implies, for odd primes p, x to the p-1 is congruent to 1 mod p. Applying this for both p and q shows that x to p-1 times q-1 is congruent to 1 mod pq. Recall that p times q is n. We can now define the RSA encryption and decryption. The RSA encryption scheme is exponentiation by e, then taking the result mod n. And the RSA decryption scheme is exponentiation by d, then taking the result mod n. We now see why n is called the modulus, and e and d are called exponents. The encryption and decryption operations are inverse operations because of the consequence of Fermat's little theorem. Let's do an explicit example. Let p be 3 and let q be 11 so that n is 33 and p-1 times q-1 is 20. We can pick the public exponent e to be 3 since 3 is coprime to 20. And we can pick the private exponent d to be 7 because then e times d is 1 mod 20. Then, for example, the number 8 would be encrypted as 8 to the 3, which is 17 mod 33. And 17 would be decoded back to 8 by raising 17 to the 7 and taking the result mod 33. In practice, the primes p and q would be much bigger, maybe hundreds of orders of magnitudes bigger than what is described here. And the messages encoded wouldn't be a single number like 8, but rather some string of characters that would be translated into a numerical representation, like ASCII, and then converted to bytes and concatenated in order to form a single number to encrypt with RSA. Why use this encryption scheme? For reasons I'll explain in a moment, it's very hard to determine d given just n and e. That way, you can share the modulus n and the public exponent e with people you may not fully trust, so they can encrypt messages to send to you, but only you can decrypt them because only you have the decryption key d. For example, every time someone enters their password on a website, the website's n and e encrypts that password, while only the server can decrypt it because only the server has the private exponent d. You can see RSA being used in real life by typing into your terminal this command that asks a site, in this case reddit.com, for its modulus n and public exponent e. It returns a result like this. Reddit indicates they're using RSA encryption, and they indicate their modulus n, shown here in hexadecimal, and their public exponent e. Your browser uses these values of n and e to encrypt your password when you send it to Reddit. Note that they do not share their private exponent d, though it is stored on their servers and is used to decrypt your password when it's received. Why is it hard to determine d given just n and e? Remember, n is a factor of two big primes p and q. If you could factor n into p and q, you could quickly figure out d. But factoring large numbers is very difficult because you have to brute force it. Modern RSA uses n around 2048 bits in length, and so brute forcing would take a long time. You can see the use of 2048-bit encryption in the real-world example from Reddit. You might have noticed two gaps in the exposition so far. If factoring large numbers is hard, isn't it also hard to come up with large primes p and q in the first place? It turns out there are algorithms that can test primality efficiently. For example, a really simple algorithm is to use Fermat's little theorem. If x to p-1 is 1 mod p, then the number is probably prime, since naively you'd only expect 1 in p random numbers to have this property. The other potential question you might have is, how do we find d? To obtain d, we have to invert e modulo p-1 times q-1. It turns out there's something called the extended Euclidean algorithm that can be used. But that's the topic for another video. Now that you know how RSA works, I'll leave you with a message you can try to decrypt.